an oscilloscope, a logic analyzer, a waveform generator, and a few other bits and pieces that you can use, so you can program the FPGA to become one of those instruments. They've provided a web interface to it. We'll log onto it just now. You can literally click whatever instrument you want. It loads the correct bit stream for you, and you've got your instrument. So it's way more versatile than just as a CASPER instrument. So here's a bit about a bit of the specs. You can see the difference between your 10, 14, and your 16 bits. The 16-bit does run the Zynq 720, and the 10 and the 14 run the Zynq 710s. You can see the difference in the RAM. Basically, everything else is very similar. In terms of connectivity, they've all got 1 gigabit Ethernet, USB 2. They claim it's got Wi-Fi, but it's an external dongle in that USB port. And you saw the synchronization connectors. You can daisy chain a couple of the boards together. But that's only for the 14 and the 16-bit. The I/O headers, most of them have, you saw them on the side, those IDE-style headers. They all have 16 digital I/O. I think there are 4 analog inputs on those I/O, but at a lot lower speed. There you go, there's your sample rate. And 12-bit resolution for those slower ADCs. So you can use this for other things, with your sensors or whatever the case may be. Your RF inputs, this is where most of you guys would be quite interested. Our sample rates across the board are 125 megahertz, with the 16-bit dropping down a little bit. We suspect it's just because of the different chip that they're using. The RF front end limits us to 50 megs, so it's a low-pass filter at 50 megs, with at least the 10 and the 14-bit having a 1 ohm impedance. And we'll just skip to the rest. The DACs, there was some discussion earlier, some of us are interested, some of us not so interested. But the DACs are interesting. It's a single DAC that is it interleaved? I think we're saying it's interleaved. So there's 2 DAC outputs, but it's a single DAC that every second sample goes to a different SMA connector. So which gives us an effective sample rate of 125. You actually clock the DAC at 250, but each independent interface is 125. And that voltage range is 2 volts peak to peak. Okay, so just a bit of a block diagram. I might have mentioned some of this already. You have the heart of the Red Pitaya, which is your Zynq ZC7, Z10, Z10. From here you can see, so that's your processor and your FPGA. You've got an ADC or 2 ADCs hanging off that. There's a single DAC that splits out into 2. You have got all those IOs, everything from SPI, UART, I2C. You have DRAM, 256 meg on the one board and 512 on the others. And I think I've mentioned most of that. The Ethernet is 1 gig, which is quite cool. Okay, so the Zynq itself, the Zynq is a SoC, and I was kind of coming here under the impression that a lot of people hadn't used FPGAs before, but judging from the last 2 days, most of you guys seem to be pretty comfortable with FPGAs and have an idea of what a SoC is. But basically, it's a system on a chip, so it's not just a single device, it's multiple devices. So you could have memory on it, you could have programmable logic, multiple processors, whatever the case is. On the Zynq, it's some FPGA fabric, programmable fabric, with an ARM, in this case, a Cortex A9. So basically, the Zynq puts both the programmable logic and the processors onto the same chip. The great thing is, if you look at our Roche boards, for instance, we used to have a separate processor, the Power PC, and a separate FPGA. Now we don't have to route that on the board. We don't have to design a board that, we don't have to create interfaces between them, we don't have to do all that. It's a lot easier to create a more compact, power-efficient board. So it's just an idea of your programmable logic. The yellow is all resources, FPGA resources. Your ARM core is hard-coded in the case of the Zynq, It does take up physical space, probably at the cost of resources, but it's there on the SOC. The other idea was, I was reading the other day, and someone saying you can even create a microblaze to hand off some of the processing to, if you have a dedicated task to do that you didn't want to do on the Zynq, you could do on a little microblaze soft core if you wanted to. So this is just an overview of the Zynq. If you read the data sheet, this is the main kind of diagram that you'll come across. And there's some very cool interfaces here. If we start off here, this is your main processing unit. There's a whole lot of bits and pieces. I'm not going to go into that. You have your DDR2 and your DDR controller. But the interesting thing is that this is your Zynq. Anything down here is your programmable logic. You have some interfaces between the two. So you've got a few general purpose interfaces. You've got your high performance ports, your programming port, I think is that one. And there's a couple of other general purpose interfaces. So you can communicate between your processor and your programmable logic. So you've got the central interconnect, which also manages all the peripherals from those I/O that we can see on the Red Pitaya, and that also lets you access those peripherals from the programmable logic as well as from the processor. Any questions on that before I move on? Okay, so when we created let's call it the board support package to add support in the CASPER tools for this for the Red Pitaya, we needed to create our Zynq architecture. So Vivado gives you tools, a block diagram tool that you can drag and drop blocks down and configure them, and they will synthesize into the processor. This is your main processing system. Quite simple in terms of the I/O that it exposes to you, but when you open it up and you want to configure it, you'll see all the configuration underneath. I'll show you now. So all we've done is we've got a processor which we can run our operating system on. We have an AXI interface. So this will give us access to our software registers that sit in our programmable logic. And then we just did some resets. We want to be able to reset the board from the Zynq. So we've just put a reset manager in there. And we generate quite important system clock, which we can use other than the ADC clock, as we were speaking about earlier. We could add support for using the system clock for your design. It gets a bit tricky because if that clock is running a different frequency to your ADC, you're going to have to do the buffering or manage the FIFO in between the two clock domains. Okay, so if we double click on this block, this is what we get. You can see here it kind of maps to this quite well. And underneath this, you can click on any of the peripherals. You can manage each of these interfaces. You can manage the clocks. You can do a whole lot of configuration here. It's actually quite scary what is available. Xilinx has done an amazing job here. That just gives you an idea of how you can configure your processor. You can see that it's actually a dual core. So when we came to porting, there's a couple of things that are quite important. Clocks and resets, and we've realized this over the years. If you don't get your clocking and reset architecture correct from the beginning, you're going to have trouble. It bites you in the most strange ways, and you end up debugging something that you think it is. Often it ends up being that your clocks are not synchronized, or your reset is a bit iffy. So kind of my advice, if you are porting to a new board, get that stuff nailed down as soon as possible, the clocking and the reset architecture. As a designer, as a user of the CASPER tools, the great thing is you don't have to worry about this. It's all kind of abstracted away from you. When you look at your design, you drop down your yellow blocks and your DSP blocks, you don't really have to worry about the clocks too much. You have to worry about routing them. They're automatically routed. That was just, again, we only support the ADC clock, not the clock generated from the processor. And as Adam mentioned earlier, the ADC clock comes in and it accompanies the data. It's the sample clock for the data. Another cool thing, just reading through the documentation, and clearly this shows you what Xilinx want to do with these Zynq cores. They've got what's called a Snoop control unit, and yes, that's, I think its official name. There's an arrow missing here that goes to the programmable logic. What this does is it allows your programmable logic to actually interact with the level 2 cache and the on-chip memory, so that you can manipulate that data without the processor having to copy it into any other memory. You can manipulate that, and you can tell the processor, okay, great, I've done the manipulation of that data, you carry on doing what you were doing with it. It's quite scary because you could get yourself into a lot of knots doing that, but it's a very interesting feature, and it just shows you that Xilinx is really targeting some form of co-processing with these processors. Okay, so just to give you an overview of the CASPER ecosystem and how we all how it all fits together. just give me how many of you have actually built the design in the CASPER environment? Okay, so there's quite a few that haven't. Okay, so this is very high level. There's no detail in this slide, but basically we created a simulating design with some blocks. An ADC, maybe an FFT, and you want to stream the data out over an Ethernet interface. You click compile, or you run Jasper. Jasper, the Python backend, or Python Toolflow does some magic on it, and it basically spits out a Vivado project, which we hand over to Vivado. We kick Vivado off on that project, and we get a bit stream out here. We run a little bit more Jasper Python magic, and we create a bit stream, which we call an FPG file, which we can upload to the CASPER supported hardware. So to give you an idea, the bit stream consists of, or the FPG file consists of the bit stream. It's got a memory map of all our software registers and our BRAMS at the front. It's got some design metadata, so you know the configuration of your designs, what options you chose on all your blocks in the design, and then the bit stream. There's a bit of an overview of the header. There's your memory map. I'll tell you a little bit more about CASPERFPGA now, but Maurice is going to go into detail on that for us. This is some of your metadata in the red. It tells you a little bit about your design. You can see there's some configuration settings. That's clearly targeting a snap board. Your clock source is your system clock, and the clock rate is 100 megs. Here we've got a bit of Git info, so it tells you what Git repository this was built from, whether it was clean or dirty at the time. And so it's a lot easier to check back and see what file or what state the repository was in when you built your FPG file. And then that's all your binary data for your bitstream. Okay, so that's kind of a bit about the build environment. The runtime ecosystem is a little bit different. We have a number of packages. So I'm going to start up here with Core 2. Core 2 is basically we use it to run our instruments. So you're running Core 2 if you're running multiple hardware platforms or multiple boards. So that's an instrument level control. What that does is it sits on top of CASPERFPGA, which interfaces to individual boards for us. So for a lot of us, if we're running a single board, we don't have to worry about Core 2. We come in at this level, CASPERFPGA. It's a Python package. I can run it in IPython. I can connect to a board. I can query registers. I can configure stuff, and I can read back data. CASPERFPGA runs over the Ethernet interface, over a network. All CASPER hardware is networked. In this case, we are running what's called TCP BORF server on the Zynq processor. Some of you who've worked with the Roaches and the further back hardware boards will know about TCP BORF server. Basically, it's just a server that we can connect to and issue commands. It'll translate those commands into either read or write interfaces over the memory map. It might program the board. It might read data out of a streaming interface. But it basically does all your control of that hardware platform. That sits on your Zynq, along with your programmable logic. In this case, all sits on the Red Pitaya. And the Red Pitaya, you've got a couple of ADCs, GPIOs, and an Ethernet interface available to you. The protocol that CASPERFPGA speaks to TCP BORF server is called CATCP. Originally stood for Karoo Array Telescope Control Protocol. So when we ported TCP BORF server, and Maurice is going to go into the details of this, I've just got a single slide. All we had to do was build it for the ARM. It was previously built for the PowerPC, so we git cloned it onto the Red Pitaya, make, build, and away we went. There were one or two changes we had to make. The way that you can program your bitstream on the Zynq is pretty cool. You've got a memory device slash dev xconfig, and you literally cap your bitstream to that file, and the drivers underneath it take care of programming the FPGA. So from the user's point of view, it's very easy. And that was a modification made to TCP Morph server to allow us to program the bitstream to the Zynq. They've done a similar thing. Your memory devices all sit in dev mem, and you just read at a particular offset for which is your address, and you can get your data back from that register where you can write. So we added programming support and read and writing of registers. And the rest of the stuff was pretty much there. And Varice is going to give you an overview just now about that. Then, when we ported CASPERFPGA, we leveraged the existing architecture that we had. Tyrone is going to give a presentation after Varice, and he's going to go into detail about this. But basically, we took an existing layer for CATCP for the Roach boards. Because we're using TCP Morph server, we could reuse this layer and target the Red Pitaya. One thing we did struggle with was Indianness. Between the PowerPC and the ARM, the Indianness was different. It took us a little while to figure this out. We weren't sure what the funnies were, why we were getting such strange data. But eventually, we managed to fix it where we were happy. CASPERFPGA also just manages our upload and programming, so it'll send an FPG file to TCP Morph server, which will then program it, and then also manages the reading and writing of the data. So if you're going to port your own board and you're interested in doing this, there's a couple of things you're going to have to do. First of all, we created a Red Pitaya Xilinx system generator block. So what this does is this block edits your system generator block and adds the correct parameters in there. So in this case, if you open up the system generator, you would see the Zynq board, the Zynq processor that it was targeting. It also sets up, in here you set up your clock speed. If you come out to the tutorials, you guys will be able to do all of this, and we'll walk you through all of this and how to set it up. So for those of you that haven't seen a Xilinx design before, that's a software register. In this case, these are all on the bus. So you can read and write these from your control side, from CASPERFPGA. There's a couple of Xilinx blocks. In this case, you're just controlling your counter, so you can write a few bits into here to set your counter going or reset it, and you can read your counter value out from software. Just a basic adder. The simulation input is 10, but you've got A and B, and you write in A and B, and you'll read out the sum of them from there. This is basically tutorial 1. So we had to add the software registers to the bus. Now, on the older boards that we've had, we've had memory map buses such as the OPB bus and the Wishbone bus. And I don't know who you are familiar with this, because this is quite down in the depth of the Toolflow. But we had to, in this case, use AXI. So we ended up borrowing some code from Matt and the guys in the corner there. They'd written some really cool AXI memory map kind of creation stuff. So it'll create your interconnect and all your devices hanging on that interconnect. And we've integrated that into the tools. So we, so each of these registers gets an address on the bus, and then we kind of, when we generate the interconnect, it gets assigned that address, and that gets stored in the header of the FPG file, so you can address each register by name, not just by address. Yeah, so another thing we've also done is, so that's the memory map objects that I was talking about. We've also added support for the BRAMS. We have software BRAMS that are on the bus as well. You can drop that down, and you can. We've got these blocks called snapshot blocks where you can trigger them and then read out the data in the BRAM. So these BRAMs also have to be on that AXI memory mapped interface. We're busy working with Matt at the moment to get this raw AXI light interface working, but let's not go into that. So when we generate the memory map, this is what we spit out, and we give to Matt's tool. So you can see here, in this case, our primary offset is 400,000 hex. And we've got two, call them devices, a sys block, and then we've ganged all the software registers together, sitting at different offsets. And each of them has their own internal memory map. So we've got a kind of a two-layer architecture. Inside the software registers, you can see we've got 5 software registers here, each of their own offset within this offset, and they've each got a name. We give it a few other parameters, such as is it readable, writable, or read and writable, or whatever the case is. And we pass this stuff off to the tool, and it goes away and generates our HDL interconnect for our AXI memory map bus. We take that and we wrap it up and we put it into your project, your Vivado project, and it automatically gets connected up correctly. Okay, one other thing we did was Adam did a lot of work on the ADCs and the DACs, so he created the yellow blocks for those. Here's just not really the full circuit diagram, but you can see here your jumpers for your ADCs, where you can select the 1 or 2 volts peak to peak or the 40 volts peak to peak, coming through some filtering and through the amplifier circuit, which they haven't disclosed here because it is actually closed source in terms of the circuit, through some differential pairs and into your FPGA. Here is a design with the FPGA. So if you're going to use the FPGA, you drop down this yellow block. You've got a couple of outputs here, your I and your Q data. Sorry, data valid, your I and your Q. This is the second tutorial on the Red Pitayas if you're interested. All we're doing here is we're taking the data from the ADC, pumping it straight into the DAC and out the other side. We've got a BRAM, which kind of does a snapshot, in this case, it's not a snap lock, which basically takes a snapshot of the data when you trigger it. And then we can read that out in software. I'm going to try and demo this shortly, so we'll come back to that. Yeah, so the work that was on the porting of the Red Pitaya, it wasn't just myself, there was a number of people. Big thanks to Adam, Amish, Brian, Mark, Maurice, Jack, and also Matt and his team for their contribution. So I think those guys at least need a round of applause for the work that they've done. Great, thank you. That's all for me. Are there any questions before I do a quick demonstration? Dave?
Did I see the input impedance to the ADC is 1 meg?
It's 1 meg on the 10 and the 14 bit, and I think it's 50 meg on the 16 bit. 50 ohm, sorry. Okay, so I am going to quickly demonstrate. How much time have I got, Dan? 5 minutes. Sorry, yeah.
How does the Zynq FPGA compare with the FPGA of Roach or
Oh, it's tiny. It's absolutely tiny. Don't think you're going to run a big instrument on it.
Okay.
This is more of a teaching aid, and if you've got some small projects, yeah, I can point you to the data sheet of the FPGA afterwards if you'd like. Cool. Anybody else?
Is there a block for DMA transfers?
Sorry, I didn't mention that. I was supposed to mention that. So if we go back to here, there are actually master state. Yeah, so there is you can do DMA through AXI streaming, which is something we were looking at implementing, but we haven't had a chance to yet. I'm trying to think. Yeah. Okay. But yeah, so the idea was actually, let me just go here. So idea here was that you can drop, ideally we want this interface to be an AXI streaming interface, that you can just put it into any DSP block that has an AXI streaming interface, but then also that you can just drop down this, let's call it like a kind of a snooping unit that you can drop down there and the data can go directly to DMA. And you can just check your data at that stage. We use these snap blocks traditionally in CASPER, but with this AXI interface, that DMA streaming would be very useful to that point.
Any progress on getting the Python packages migrated to 3?
I'm not going to answer that question. No, to Jack. Is Jack on?
What was the question?
Have we migrated any of our packages to Python 3? I heard last week that we had done a couple. What have we done?
CASPERFPGA and Toolflow.
What about Core 2? That's used too, right?
Jay?
They all depend on each other.
I don't get to speak about code.
I know that.
Jason?
So I know for tutorials we are using Python 3,
Okay.
but Jack is still working on porting into Python 3, like everything.
I think this is like only of this week almost. So
Yeah.
if you're going to use Python 3, just let us know if there's any issues, basically. Sorry?
That's amazing.
People are starting to use Core 2. Okay. So, onto the demo quickly. Whoa! Okay, so the setup here currently is I have a signal generator outputting this just a 1 megahertz tone. It's going into a splitter. One's coming to the oscilloscope. The other's going into the input of the Red Pitaya. And I'll leave this up afterwards if you guys want to come have a look at it. The Red Pitaya then has outputs that same signal over the DAC. Okay. The Red Pitaya outputs that same signal over the DAC and to the second channel of the oscilloscope. What I'm going to do is I'm going to run a script. And you'll see this if you do the tutorials. This is basically going to connect to the Red Pitaya on that IP address. The -P tells it I'm going to program it. I give it the B is for the FPG or the bit stream. And it's going to upload that bit stream to the board and then run it. This script, what it does is it reads that VRAM that you saw with the two ADCs. You saw the design with the ADC and the DAC and the VRAM in between it. It reads that VRAM and it just plots the two plots. Okay, so there's an output of, that's what's being basically input over both ADCs. Can anyone guess at what's going on here? There's no input into this ADC. Yeah, someone said crosstalk. It's tiny. I haven't got it terminated at the moment, so you can see the signal that's coming in on the first ADC. So there you can see your ADC input. And that data we've brought back to my laptop, and I've got it in Python now, and I can do whatever I want with it in Python. And then you can see the two signals on here. The yellow is our input signal, and the green is the DAC output. If you guys want to come have a look at this, you are more than welcome to.
So is this a live updating thing?
It's actually not live updating at the moment. We have scripts on the other tutorials, I think, on the spectrometer tutorial on the Scarab does that. But we haven't had a chance to do this yet. Right.
Interesting. The programming time was so short, actually. Like you just click enter and just pop up.
It is very
Like too small. Because the file size is small.
the file is tiny.
Okay.
Yeah. First of all, it's a small design, and also it's because it's a small FPGA. You're never going to really have large instruments.
Okay.
So is the other channel some little bit of crosstalk?
Yes, yeah. So that's just crosstalk. Yeah. I haven't terminated it. So.
Is the board running Linux right now? Or?
The board is running a flavor of Linux that's called Pitaya Linux. I think Xilinx has created the kernel themselves, and there's some drivers that come along with that.
And then that work server runs on top of it.
TCP Work Server is just a service or a process that runs on top of it. I can SSH into the board right now. We can look at what's running on it as well if you want. Yeah.
How easy would it be to interface another, say, gigabit module to stream or delete?
Another what, sorry?
Another gigabit module or something to stream or delete?
Gigabit module.
Yeah.
So to stream this data out?
Yes.
So we've left that up to the community. We've kind of got the ball rolling on this.
Yeah.
We've got other projects that we need to start working on because this is not something that we use at the office. The idea is that this is a teaching aid. We're going to put it out there. If anybody has other applications for it, you're more than welcome to come help us develop. We'll give you as much support as you require, but we haven't actually been able to do that yet.
You said there were Xilinx software blocks that you could write values to for the registers.
Yes.
Is that, do you set those values in the FPG?
So you can set the default value if you want when you create your design, or when you start running the startup script, you can write the value.
Okay.
Does that answer?
Yeah, I think so.
We can chat some more with the tutorials.
Okay.
Great. Thank you very much.